Okay, looks like we're recording and the audio seems to be working, so off we go. Last time we were talking about multivariable optimization. So reminder, here's the big concept. If you're at a point where certain conditions are satisfied, namely not only is the gradient pointing in a direction, but furthermore the function's differentiable, so the gradient's actually telling you something meaningful. It's pointing uphill on the graph. This cannot be the maximizer point because it's never uphill. It's never steep at the top, right? It's always level at the top. So that's a big idea. We can eliminate points by looking at these kind of criteria. So what that means is that when we find critical points are where that elimination process fails. So it's not that we are actually concluding something about these points. It's that these are the points where we can't conclude that they're not the maximum. Right? So maybe they're the maximum. But the point is that really what's going on is that we just don't know what's happening at those points. Okay, so we call them critical points. We check them out later. We talked about the counterexamples last time. Okay, so here is an example to start with. Let's look at this function right here. And notice it's defined at every point in R2. It doesn't fail to be defined anywhere. And every point in R2 is in the interior of R2. There's no boundary to R2, right? The XY plane, it just goes on forever. So the following analysis applies to every point in the domain. Now again, we have to check two things. We have to check first, where does the function fail to be differentiable? This function right here. It's a polynomial. Polynomials are differentiable everywhere. Old fact from earlier in this chapter, but quite a while ago in this term. Okay, so there are no critical points from the differentiability condition. Okay, next, where does the gradient fail to be non-zero? Said differently, where is the gradient equal to 0? Okay, well, you take this function here, and you can compute the gradient. And if we want to know where is the gradient equal to 0, that means I need to ask where is this algebra here equal to 0. And altogether, you can look at this one coordinate at a time. And this right here definitely tells me that the y coordinate has to be 0. Right? It says 2y equals 0. That means y has to be 0. And then looking at this algebra right here, 3x squared minus 3 equals 0. Okay, well, you can solve for x, kinda, but there are two possibilities. And x could be either 1 or negative 1. Right, so we actually have two grand total critical points. Okay. Everybody see how that worked? Okay. All right, now, so what do we conclude from this? What does this actually tell us? Right? Why were we looking for critical points in the first place? We probably wanted to know where the function was as big as possible or as small as possible, something like that, right? So the fact that these are critical points does not tell us that these are maxes or mins. I remind you, right? All this was just a process of elimination. These are the points that were left over after our deductive process of elimination. We don't know anything about what's going on at those points. They may or may not be extrema. They may or may not be global extrema. Now we got to distinguish between local max and global max. A local max is like a mountaintop, right? It's just, it's the highest point nearby, right? A global extremum says this is the highest point on the entire graph, right? So some hill, out west in North Carolina, the top of that is a local maximum. The absolute maximum is only at the top of, I think it's still Mount Everest, but it changes from time to time, at least in measure. Anyway, you know what I mean. Okay. Now here's an uglier question and a pretty serious problem. Does a global maximum even exist? let's not make the mistake of doing a process of elimination to answer a question that does not have an answer. Right? It's an easy mistake to make. Now, here's a single variable version of this. Let's look at, I'm going to do this in red because this is a dangerous problem. Let's look at f of x equals x cubed. Let's find the maximum value of this function. Okay, well, the maximizer would have to be a point where f prime would need to equal to 0. And that gives me only the point x equals 0. So I guess that must be the maximizer, right? Or well, maybe it's the minimizer. It's got to be one or the other, doesn't it? No, right? Not even close. This function gets arbitrarily large, and it also gets arbitrarily, negative, right? So x equals 0 is neither. But it was even though it was the only point left over after our process of elimination, right? So this should be a disturbing example. When you are doing a process of elimination, you can only conclude something about the leftover points if you know the thing you're looking for actually exists in the first place, right? Does that make sense to everybody? The reason that this leftover point isn't a maximizer is because there was no maximizer at all. And I think there's an analogy to, y'all know the find the ball, or maybe they do it with cards, and it's find the queen, and there's cards moving around, and of course the queen gets palmed, right? There is no queen, right? So process of elimination does not resolve the question of where's the queen, right? It's the same kind of thing here. Okay, so nasty question. How do you know a maximizer even exists? And there is a theorem about this, and here's how this theorem works. What you need is for your function to be continuous. You need for your domain to be closed. That means it has to include all of its boundary points. And your domain has to be bounded. It can't run off to infinity in any direction, or said succinctly here, you have to be able to fit it inside of some ball, or even easier perhaps, you have to be able to put it in a box. If you can't fit it into a box, then it's not bounded. Does that make sense to everybody? Okay, so these three conditions, right? So we've got continuity, closed, and bounded. If those three conditions are satisfied, then f does attain a global maximum value. There is a maximum value, and it is achieved somewhere in the domain of that function. Okay, but you got to have all three of these conditions. Okay. Roughly speaking, each one of these conditions sort of eliminates a nasty counterexample that in which there would be no maximizer. And just a couple of quick examples. Why do we need continuity? Well, if we didn't have continuity, then our function defined on a closed and bounded domain here, if the function were not continuous, there could be a vertical asymptote like that. Right? So this is the kind of thing that can go wrong if you don't require continuity. Okay, why do we need for the domain to be closed? What's the big deal? Whether it's closed, that just refers to sort of one endpoint, right? Who cares? Well, if that is not closed, then there's this possibility. You could let me try to do a better job. You could have a vertical asymptote at that endpoint. This is still continuous. It is continuous everywhere in its domain. We're not responsible for what's happening at the open boundary point because that open boundary point is not part of the domain. This function's perfectly continuous, right? So because there's an open endpoint, that's why this bad thing can happen. So again, that's why we need it to be closed. Why do we need it to be bounded? Why can't we just have the domain? Whoa, what did I just do? Whoa, okay, I don't know what's going on here. There we go. Okay, why can't we just have the domain just go on arbitrarily, infinitely, in some direction. What's with the bounded thing? And, well, the counterexample there is if you allow this, then here is a perfectly continuous function that's just going to get bigger and bigger and bigger and bigger, and there, again, no maximum achieved. Right? So these three counterexamples, roughly speaking, are what we're eliminating by requiring these three conditions. And with those possibilities eliminated, as it turns out, and I'm not going to prove this, but with those problems eliminated, there are no other problems, and such a function will always have a maximizer. Cool? All right. Okay, now I do want to point out sometimes the algebra is harder than that first example that I showed you. Let's see how it might work out. So, for example, let's suppose, once you take the gradient and you set the gradient equal to 0, and you find yourself at that stage where, okay, now I just want to solve for x and y. Let me point out that things can get weird. It is tempting to look at this equation that says that 3 times x squared minus y squared must equal to 0. And, of course, that means that x squared must equal to y squared. And it's tempting. High schools sometimes even let you get away with that, to think that that must mean that x is equal to y. And it is just not true. It's not even close to true. Right? That's just bad high school. Right? So not true at all. If x squared is equal to y squared, that means that either x could be either y or negative y, either one. And there's no reason to believe, or at least not in this case, there's no particular reason to believe that any one of these cases is any better than the other. So what do you do algebraically? Do I write down x equals y, or do I write down x equals negative y? And the answer is you have to do both. You have to consider each of these cases separately. It is possible that x is equal to y. And so you got to, do all this and see what happens in that case where x equals y. But it is also just as possible that x could equal to negative y. And you got to do what you got to do there, too, and see what critical points come up there as well. Both of these cases are relevant. Any critical point that you get from considering either case, critical points, right? Definitely. If you only consider one of these cases, then you have not finished your elimination argument, right? And that's a pretty gaping hole in the reasoning. And again, I remind you, it's not about the answer, right? Let's suppose that the answer, for whatever reason, anyway, let's not worry about it, but let's suppose that the absolute maximizer is this one, right? But you didn't do case 2. Well, again, it's not about the answer. It's about the reasoning. The fact that you got the answer is irrelevant to the fact that half of your reasoning is missing. Well, not half, but anyway, a lot of the reasoning is missing, right? And so, again, you got to keep in mind that grades are about the reasoning, not the answer. So please do be careful to make sure to give me all the reasoning, and that means, for example, consider all the cases. So let's start with case 1. Let's start with the possibility that x might equal to y. What do we do with that? How do we proceed? Well, if x is equal to y, I could plug that into this thing here that has to equal to 0, right? If that has to equal to 0, and if x is equal to y, well, that means that 6y squared plus 6y is equal to 0. And, for example, that means that this has to equal to 0, just factoring it, right? And that gives you these two possibilities for y. And now what does that tell me about x? Well, what that tells me about x, I get from plugging back into the case. And if I know what y is, then I also know what x is, because of which case I'm considering. Anyway, altogether, that gives me these 2 points. Everybody with me? Okay, but now, again, that was just case 1. All right, we're only halfway done. Right? We also, just as importantly, have to consider case 2. Case 2 says x equals negative y. Now, that changes how the algebra works out. When you plug in x equals negative y into, the fact that this has to be 0, right? Plugging in x equals negative y gives you different algebra over here, right? Now, just think about what happens. If x is equal to negative y, then that first term is negative 6y squared, not positive. So you get a little bit of different algebra to solve that gives you different values for y. And let me clean up the mess here. So now I know y is going to have to be one of these values. Again, what does that tell me about x? Well, this tells me what my x's are. And so sure, y could be either 0 or 1. But in those cases, given that x is equal to negative y for case 2, x would be correspondingly the negative of those y values. How we doing? Everybody follow that? Okay. All right, so again, grand total, all of it counts, right? All 4 of these are critical, well, 3 of these are critical points. We had a double count, but that's okay, right? The origin is a critical point and still a critical point. Okay. All right, so 3 critical points. Okay. Moving along. Okay, how do we classify critical points? How do we decide if they're local maxes or local mins? I want to remind you how this works in single variable calculus. Now, there's different points of view on how to think about this. As I've done several times in this course, I'm not going to take the point of view that might be most familiar to you. I'm going to give the point of view that's most useful to us in generalizing to the multivariable context that we're actually interested in, right? So I want to take a point of view of the second order Taylor polynomial. You'll see why in a minute. Okay, so here we are with the second order Taylor polynomial for a single variable function. And I hope everybody remembers this business, right? So anyway, there it is. There's the Taylor polynomial. Now a critical point, right? Let's look at what happens when f prime is equal to 0. Well, if f prime is equal to 0, this whole term goes away. Right? Our Taylor polynomial then is just that. That first order term just disappears. And so now I want to decide, okay, well, this function, at the point A, is this a local min or a local max? Well, good news. This right here is a constant. So how this function is behaving, whether it's sort of curving upward or curving downward, or whether it's behaving like a local min like this or behaving like a local max like that, it's entirely determined by what's happening in this term right here. So this is really all we have to look at, is this one term. And okay, well, gosh, that's nice, because this term's really easy to understand. I'll notice in particular that the 1/2 is always positive, right? And x minus a quantity squared is positive unless x equals a, but we're interested in how it's behaving away from a, so that's also positive. And so really the only question as to whether this term is always positive or always negative comes down to whether this f double prime is positive or negative. That's it. And if you think it through, you get the second derivative test that you're already familiar with. If that second derivative is positive, that means that this term is always positive, which means the function has to be curving up because the function's bigger around a compared to at a, and that means it's a local min. And then likewise, if it's negative, then this term is negative. That means it's curving down. That means you have a maximum. So they're all the familiar single variable second derivative test. How are we doing? Is everybody with me? So we would like to do an analogous argument. Now in the multivariable case, it does change quite a bit. The second order Taylor polynomial is actually a much more complicated critter Taylor series in general for multivariable functions, much more complicated critter. In fact, we're only in this class going to entertain functions of 2 variables. Things get weirder when you have more than 2 variables. And it's, there's rules for this, and you can, find them written down in a book, and you can even follow those rules. So that's fine and all, but all I want to make sure we're good with in this course is when there's exactly two variables. So that being said, here's what the second order Taylor polynomial looks like. You're going to recognize some of this. Notice that these 0th and first order terms, well, that's just the linear approximation. We've seen that before. That's our old friend. It's exactly the linear approximation, right? So that's encouraging, right? Just like in single variable calculus, the pattern sort of continues. Where things get weird is when you look at the second order term. This second order term is not analogous exactly to the single variable case. There is a matrix in here. It's called the Hessian matrix. That Hessian matrix multiplies by x minus a, and then whatever the result of that is, you dot with x minus a. Now, you will see a certain amount of an analogy there. It kind of looks like, well, there's 2 separate factors of x minus a. I guess that's kind of like here we had 2 separate factors of x minus a, right? The difference is that in here the algebra is such that I can't just sort of bring them together. This is not x minus a dot x minus a. You got to multiply by the Hessian matrix first, and you can't algebra your way around that and sort of, okay, but surely I got to rewrite this in terms of x minus a dot x minus a. No, you absolutely cannot. It's just a more complicated thing. So if you've had a course in linear algebra, you might recognize this expression. This expression is called a quadratic form. If you have not had a course in linear algebra, no problem. You don't need to know that. But anyway, the algebra of quadratic forms is something that can be studied, and it's significant linear algebra, I'll say, right? It's the kind of thing that you would only really have the tools to analyze near the end of a course in linear algebra, right? So this is not something I can really wave my hands at in this context. But here's the punchline. This is how it breaks down. Again, quadratic forms are weird, but this is the resulting second derivative test. It breaks down first by looking at the determinant of the Hessian matrix. A reminder now, the Hessian matrix is this matrix in here, but more specifically, the Hessian matrix is this formula. It's the matrix whose entries are the second partials of your function, organized in the obvious way. That's just how this all works out. Right? Okay, so you got to look at the determinant of that Hessian matrix and take it from there. Now, if the determinant is positive, then you look at these rules. And this is what you might call the familiar part, because you notice then that the sort of the I guess you might call it the second derivative. That's an unfortunate choice of terminology, I guess, right? But the XX second partial, positive implies a min, negative implies a max. It looks just like the old second derivative test. How about that? Handy. But very importantly, and you got to remember this only applies if the Hessian determinant is positive. If the Hessian determinant is negative, totally different set of rules. If that Hessian determinant is negative, then you absolutely stay away from that. That's got nothing to do with anything. If your Hessian determinant is negative, totally different conclusion. You actually have a saddle point, no matter what. The function has to be appropriately regular. Again, I don't want to get bogged down in that stuff. Yeah, you see the importance of the Hessian determinant there. It tells you in some sense which rule to use, arguably. Okay. And then, of course, there's a third possibility. The Hessian determinant could be 0. If the Hessian determinant is 0, this is a bad news deal. It means that you're kind of on the edge of different primary possibilities, and a bunch of weird tertiary oddities can come up. And it's not that we can't revise our test to address all of the other, again, various possibilities. It's that we don't want to. And so when the Hessian determinant's equal to 0, we just throw up our hands and say, you know what, this is too weird for this test, and so we're just going to declare that the test comes to no conclusion. And since the purpose of a test is to come to a conclusion, I think it's fair to say the test fails. Yeah? Everybody happy? Okay, so you just got to memorize these rules. These are not intuitive, right? Don't look for, oh yeah, geometrically it's satisfying that it works out this way. No, absolutely not. There's sophisticated linear algebra behind this, and you cannot just kind of intuit your way through this. You just got to memorize this set of rules. So here we go. Let's see an example. Previously, we looked at this function right here. We found 2 critical points, and I reminded you at the time that we have no earthly clue, based on the mere fact that these are critical points, what the function is actually doing near these points. Right? But now we have a second derivative test to try to help us. So, okay, let's play the game. And let's see, I am going to zoom out here so I can try to get this all on the screen at once. There we go, close enough. So let's start by considering this point right here, 1, 0. So I've got to take this and plug it into my test. My test says I'm going to need to know what the Hessian determinant is, whether it's positive, negative, or 0. Okay, so, well, let's compute the Hessian determinant. Here's the formula for the Hessian determinant, and you'll notice that for this point, right, plugging in this point, x being 1, that Hessian determinant is positive. So, because the Hessian determinant is positive, that means that I look at this part of our chart. Everybody with me so far? Yep.
If it's got a variable in it, does that mean that it's positive, or are you only looking at the coefficient?
Well, we're looking at what the value of this Hessian determinant is at the point that we're looking at. So you got to keep in mind. So I'm not asking if the Hessian determinant is everywhere positive or everywhere negative. I mean just at the point that we're entertaining. Is that cool? Everybody happy? Okay. All right. So next question. It says here that I've got to look at the fxx. Okay. Well, conveniently, by the way, notice fxx is the top left entry in the Hessian matrix. So you've already computed it, right? Here it was in this process, top left entry, 6x. Again, we're only interested in what happens when you plug in our point, 1, 0, and at that point we find that fxx is 6, which is positive, and that tells us that we have a local min. Everybody see how I went down the flow chart, as it were? All right, now, of course, all of that only applies to this one point that we were looking at, right? We were just looking at 1, 0, so it's only 1, 0 that I get to conclude is a local min. So now let's consider this other point. Let's consider negative 1, 0. And again, we got to play the same game. I'm going to try to plug this into the rule, see what happens. Well, again, I've got to compute the Hessian determinant. Again, I already have a formula for the Hessian determinant, so I need to plug in this point into that formula. X being negative 1, you see that Hessian determinant ends up being negative. Right, again, we're at the point A2 here. Okay, so negative. All right, so I come up to this chart, and here's where the Hessian determinant is negative, and end of story saddle point. So that's a saddle point of some sort. And it could be, who knows? It could be a regular Pringle-like saddle point. It could be a monkey saddle. It could be a spider saddle. I bet you could imagine what that would look like, right? All sorts of weird possibilities. Who knows? But it's definitely not a max, and it's definitely not a min. Yeah? Okay. Real quick, I do want to admit to some shortcomings of this second derivative test. Notice that it doesn't address the possibility of what if fxx equals 0, right? If that happens, what does that mean? Well, again, the test fails. We're just not addressing that at all. Okay. Okay. Moving along. Let's see here. Whoops. Okay, there we go. Okay, so everything we've talked about so far has been in the interior. Reminder, every set has an interior and a boundary, right? And we're going to have different rules for the interior and different rules for the boundary. We are now going to move to the boundary. For reasons I'll explain in a moment, we call this constrained optimization. How would we represent a boundary? Well, very often it's with an equation. So for example, if your set that you're interested in is the unit disk, such as this right here, right? There's the unit disk. Well, what's the boundary? The boundary is like this right here. Oh, yeah, that's the unit circle. And again, we can represent the unit circle with an equation. Now, to be fair, there are other circumstances in which it might not be convenient to represent a curve with an equation. Granted, the method that I'm about to show y'all, called the method of Lagrange multipliers, works when your boundary or whatever domain that you're considering is described with an equation. So those other circumstances will require other methods or will require you to adapt and represent the curve as an equation. Okay. Now, this is a two-dimensional example. What if we have a three-dimensional example? What if we have a unit ball, for example? Well, the boundary of a unit ball is a sphere. Right? That's what the boundary is. And again, represented with an equation. So now keep in mind the sort of the geometry of this. This means that if you have three variables in your optimization, that means that your boundary consideration is going to be on a surface that is represented by an equation of three variables. Whereas if you have a two-dimensional optimization problem, your boundary is a curve, which again will still be represented by an equation, but now, of course, just an equation in two variables. All right. Okay. A little bit of terminology, and this is going to be very useful. When you have your boundary represented by an equation, that equation is called the constraint equation. Now, very importantly, the way this method is going to work, we need this equation written in a certain form. We need this equation to be written as a level set. So you'll notice in this case it already is. I don't even have to fiddle with it. I don't even have to move terms around or anything. That was lucky. Sometimes you might have to move terms around, but we need it to be written as a level set. In other words, as stuff equals constant. This function, whose level set we're looking at, that function is called the constraint function. So we have two bits of terminology here. We need to understand the constraint equation, and we need to understand the constraint function. Is everybody on board? The constraint function is a function whose level set, one of whose level sets, is the constraint equation. Okay. By the way, of course, there are multiple ways to do this. I mean, I certainly could take this equation right here, and I could rewrite it equivalently as x squared plus y squared minus 1 equals 0. This, too, is a level set of a now different constraint function, right? So which one is it? And the answer is it doesn't matter. Do whatever works most conveniently for you. In a lot of books, just for convenience, just to keep things simple, they'll rewrite things. Oh, I just erased what I needed. They'll rewrite things in such a way that the constant over on the right is 0. That some reasons that's considered convenient, but it's not essential. It doesn't matter. And you'll notice I didn't bother in this case, right? In this case, all that would do is add an extra dangling constant term in my constraint function, and I didn't want to deal with a dangling extra constant for no reason, right? And so I just left the one over on the right-hand side. Is everybody happy? Okay. All right. Okay. So, constrained optimization, the method that we're going to talk about here. The question will be that there is some function that I want to maximize. The constraint is that some other function has to be a constant. This is confusing. There are two functions in play. Right, there's the function that I want to maximize, and there's the function that's not allowed to change, that serve different purposes. G tells me which x's I'm allowed to consider. F is what I want to consider with respect to those allowed x's. Does that make sense to everybody? The function we're trying to maximize is constrained by the fact that the constraint function tells me where I'm allowed to even look at that. All right, so do make sure to keep these distinct in your mind. By the way, this function f that you're trying to maximize, sometimes called the objective function, and we've already referred to g as the constraint function. Okay, so just as a for example, you might say, let's maximize this function. Let's try to make this function here as big as possible. Before the sentence is even done, there's a temptation to say, hey, you can't maximize that. Just let x keep getting bigger and bigger and bigger. This function can get as big as you want. There is no maximum, right? But the question is to maximize it on the sphere where x is not allowed to get bigger and bigger and bigger, nor are y and z, right? And so on the sphere, maybe there is a maximum value to be found. Everybody on board? Okay. So in this case, my objective function is this. My constraint function is this. Everybody happy? Notice I get to say that this is the constraint function because this right here is, setting that equal to a constant, namely that makes this a level set of that constraint function. Okay. Okie dokie. So, how are we going to do this? I'm going to make a couple of clever observations here. First observation, keep in mind our constraint is that our constraint function has to equal a constant. So I'm looking at a level set. That's an equation. By the way, I have a picture here assuming that I have three variables, namely that this is an optimization in three-dimensional space. So this level set, being an equation of three variables, is going to be some sort of a surface. Okay. Notice further, if I were to talk about the gradient of that constraint function, those gradients, we know cool information about gradients in relation to level sets. Again, very importantly, this is a level set of this function g. That's how we define g in the first place. right? And the cool fact that we know is that gradients are always perpendicular. Well, orthogonal. They could be zero, right? But anyway, right angle or zero. So orthogonal to the constraint set. Is everybody happy with that? Okay, so with that observed, let's now ask what does the gradient of f tell us? And I want to make this observation here. Let me talk about the setup first, though, real quick. Okay, so again, here's my constraint set, aka a level set. Here's my constraint gradient. By the way, that's some common and convenient lingo. Constraint gradient as a shorthand for gradient of the constraint function. Conveniently perpendicular. Let's play the game. What does this gradient right here tell me? The fact that gradient of f points that way. Well, I just, innocent observation, if that's the direction that the objective gradient points, gradient of f points like that, well, look, man, I can just start moving this way along my surface. Now, the temptation is to be able to say, this is the direction that the function is increasing the fastest. F is increasing the fastest like that. Why wouldn't I just go in the direction of the objective gradient itself? And the answer is because you're not allowed to, right? You're stuck on the constraint set. You're confined to that surface. So that's not really on the table. What you can do, though, is kind of drop a perpendicular to the tangent plane, and you can say, I'm going to go that way. And now, just a quick geometric appeal, that makes this an acute angle, right? That theta right there is an acute angle, and I can then ask, okay, well, how fast is the function changing? How fast the function is changing is determined by, and I'm already out of stylus power. Okay. Fine, let me plug this back in. Let's see here. So gradient of f is that blue vector. I'm going to be dotting that with v. I wanted that in purple. Dotting that with v. That's my velocity vector. And you can see that my directional derivative here, how fast is the function changing as I move in that cleverly chosen direction along the surface? Well, it's this dot product. It's blue dot purple. That's an acute angle. That dot product is positive, as drawn. Does that make sense? And then I'm going to repeat the same sort of innocent observation that we made when we were talking about regular sort of interior unconstrained optimization. Hey man, if your function's still getting bigger, it's in the process of continuing to get bigger, you're not at the top yet. The function's not as big as possible. It's still increasing. Does that make sense to everybody? Okay. All right. So this is our process of elimination. We had to go a little bit more trouble here to create a process of elimination. Let me remind you that going back to the interior argument. The interior argument, well, if your gradient is non-zero, that kind of ends the story, but just go that way. Right? And that means I can eliminate that point as a possible maximum. So here, again, you got to go to a little bit more trouble. Oops. But again, we have an argument that eliminates this point as a possible maximum. So great, I can eliminate lots of points. My boundary is an entire surface. I don't want to have to go through one point at a time and eliminate them one at a time, right? What we want to do is ask ourselves, what could possibly make this argument fail? Right? And there are several assumptions that went into this argument that we need to acknowledge. The failure of those assumptions will answer our question of how could the argument fail. And I assumed in here that the function was differentiable. So if it isn't, then this whole business about I can compute directional derivatives with that formula, no, you can't. Not if the function fails to be differentiable. Function fails to be differentiable. This doesn't mean squat. The dot product doesn't mean anything. The fact that the dot product's positive, who cares? That's nothing. Right? So failure of differentiability would make our argument fail. Likewise, I was assuming, and I kind of swept this under the rug on purpose, but I was kind of assuming that my objective gradient was not perpendicular to the constraint set. See how I drew it off at an angle like that? I didn't draw it perpendicular to the constraint set like the gradient of G is. I drew it off at some angle. What do you think would happen to the argument, though, if instead of this, what if my gradient of f was like that? How does the argument fail? Well, the argument fails a couple of different ways, but most dramatically, that I can't just drop a perpendicular. If I try to drop a perpendicular, I get zero. That doesn't point in a direction. That doesn't prescribe a direction that I can move and make the function obviously increase. I don't have any direction at all. So I was assuming, and my argument would otherwise fail, I was assuming that it's not perpendicular to the constraint set. And if it is, my argument fails. Yeah? Okay. All right. And then lastly, and this is arguably silly, but we got to worry about these kinds of things. I was also assuming the gradient isn't the zero vector. If the gradient of f is the zero vector, and again, then I have no direction to point, and my dot product was going to be zero anyway, and again, the argument fails. Okay, all right. So one could make the case that this is one way to formulate a definition of critical points. These are the points where our argument fails. Now, these are hard to work with. In particular, this one right here is hard to work with because we don't have any convenient algebraic tools for deciding when a vector is perpendicular to a set. Right? So that's annoying. But if you look at this picture, and let me clean the picture up again real quick. We've already agreed long ago that the constraint gradient is always perpendicular to the constraint set. So this possibility that the objective gradient might also be perpendicular to the constraint set could be rephrased as these two vectors being parallel to each other, or one of them being a multiple of the other. And that's algebra that I can write down pretty easily. Two vectors pointing in the same direction. Let me sloppily say, okay, that means one is a multiple of the other. Write it down. Nothing to it. One of those vectors is a multiple of the other one. Right? So this is a much better set of conditions, and I know that they don't look the same other than this one little trick. There is also the business about, hey, why didn't I keep that condition? Right? Well, why didn't I keep that condition? If the gradient of f is equal to 0, doesn't that really kill the argument? Am I not worried about that here? Well, I actually have that on here. That would be caught by this condition right here. Right? If the gradient of f is 0, the 0 vector is a scalar multiple of the gradient of g. That scalar is 0. Totally fine. Lambda is allowed to be 0. No problem. Right? So we have not dropped condition 3. We just sort of absorbed it into this this second condition down here. Is everybody with me? Okay. Okay. So what about this bit? Oh, whoa! Hang on. I was trying to erase. There we go. What about this business about gradient of g? being 0. Why am I worried about this all of a sudden? And that's got to do with this picture down here. If the gradient of g is equal to 0, such as this, then the picture that I had drawn of, the gradient of g is like this, and the gradient of f is like this, and so, the gradient of f is clearly a multiple of the gradient of g. Well, in this case here, the gradient of g being 0 doesn't define a direction perpendicular to the surface. It's still orthogonal, but it's not perpendicular. And again, zeros are annoying, and this is the kind of issue I have to worry about. So basically what I have to recognize is that if this happens, if the gradient of g is equal to 0, such as in this case, then this just doesn't apply. And my multiplier equation there, gradient of f equals lambda gradient of g, that would fail to catch a perfectly good, perfectly good orthogonal to the surface objective gradient. So anytime the gradient of g equals 0, I have to put that, I have to call that a critical point, because otherwise I would miss this case. Is everybody with me? Okay. So nice punchline. I get to exchange these three conditions here that I originally had, but that I don't like because they're algebraically hard to work with. I get to exchange that for these three conditions, which, by the way, are a little bit looser. If we use this little trio down here that we like better because it's algebraically more workable, we are going to find more critical points. We're going to have a little bit more to deal with, but at least the algebra is doable. So this, in practice, is what we call critical points, and this is called the method of Lagrange multipliers. By the way, pronounced Lagrange, not Lagrange. There is a small town in Texas called LaGrange, and if you ask anyone there how to pronounce it, they will say Lagrange, but the French mathematician did not agree. He pronounced his name Lagrange. Lagrange multipliers. This right here is the multiplier. That's why they call it Lagrange multipliers. It's just because of that scalar multiplier. That's all it is. And we call it lambda because of the L in Lagrange. Yeah? Everybody happy? Let's do one. Let's get our hands dirty. Alrighty. So we've got an objective function that we want to find critical points of. I want to know where this is, as big as possible or as small as possible, whatever. We want to find the critical points. And let's see here. We're going to do so on this, on this constraint set, which you'll notice, again, written as a level set, thus making this my objective function. Anybody good? Before I do this, why don't I quick revisit a point that I talked about earlier, just to kind of connect the dots. I'm going to see if my stylus is working again now. I'll bet you it is. Let's see, how's the battery on it? Yeah, we're all good. Okay, so we started this discussion by talking about how, we have to be able to entertain our boundaries. Notice that this surface this surface right here is not a boundary. It's an entire plane. If you think about it, even though we came into this motivated by entertaining questions about boundaries, our analysis never made any such assumption. I never assumed anywhere in this argument that my surface was actually a boundary of some region. I never assumed that this was a closed surface. So even though, again, we came into this motivated by thinking about boundaries, in fact, we have a method that applies for any set described by an equation. So we ended up inadvertently with more than we had planned. Okay. Yeah, okay, so here we go. We have our objective function, and we can compute its gradient. We have our constraint function, and we can compute its gradient. Now let's go through our list of conditions. Our list of conditions, here it is. Okay, our list of conditions, I've got to check, is f always differentiable, or does it fail to be differentiable anywhere? Then I have to write down the Lagrange condition. And then I have to write down, by the way, this one here is called the degeneracy condition for reasons that are much more advanced than this course allows discussion of. But you're going to hear me call this the degeneracy condition. Something bad can happen to the surface when this happens, basically. Okay, so we got to check these three conditions. Here we go. Okay, f, clearly differentiable. It's a polynomial, no issues. Fine. Is our constraint gradient ever zero? Nope. Easily observed. 6, for example, is never zero. Right? For any value of x, y, or z, 6 will always be non-zero. Likewise, 3 and 2, of course. Okay. So we've checked conditions 1 and 3. By the way, real quick, most of the time, your function is going to be differentiable and the constraint gradient will never be zero. Most of the time. Again, I remind you, it's not about which of these conditions will lead me to the point that ends up being the maximizer. That's not what we're interested in. We're interested in a complete argument. And again, for your elimination argument to be complete, you have to actually consider all three of the conditions, right? So it is tempting, very tempting for students to kind of, but I want to get on with it. I want to get down to where the answer is because I got to put a box around it, right? And it's a very strong urge, I know, but you can't do that. So many students will just forget to even entertain the question of whether the objective function is differentiable. And that's a problem. Your argument is incomplete if you don't doff the cap. I mean, it's so easy to do, right? Glance at your function, confirm that, it's differentiable, and then write down f diff, right? I mean, you could be as terse as you want to be. But if you don't, then you left out part of your argument, and it is significant. So there's that. Likewise, take a glance at your constraint gradient, and just, usually it's pretty easy to recognize that it's not zero. And just, again, doff the cap. Just write down gradient G not equal to 0. And your argument's more complete. Okay, so here then is the remaining condition, the Lagrange condition. The gradient of f has those coordinates. The gradient of g has these coordinates. And so altogether, this Lagrange vector equation turns into this trio of equations. Now, let me remind you, the purpose of the Lagrange condition is to entertain points on our surface. We're only interested, in the first place, in points that are on our surface. So, specifically then, I need to understand points that satisfy these 4 equations. If there is some point way over there, it's not even near our constraint set, that coincidentally satisfies the Lagrange condition, who cares? It's got nothing to do with our question. We're only interested in points that are on the constraint set. Is that satisfying? Okay. All right. Easy to forget also. Okay, so now begins the algebraic fun, and there's different ways that this can break down. Very often, though, what you want to do is solve for lambda. And keep in mind that every formula that you get for lambda, they're all formulas for the same lambda. So if lambda's got to equal to all 3 of these things, then all 3 of these things have to equal to each other. So this is called eliminating lambda. You solve for it in all 3 equations, set those things equal to each other. Does that make sense? So now, having eliminated lambda, I now have 3 equations and 3 unknowns. All right? Don't forget about our constraint equation, of course. But then I have just this sort of what you might call trio of equations. And this isn't that hard to deal with. What I'm going to do here is I'm going to solve for y and z in terms of x. So that gives me that. That gives me that. And then I'm going to take these formulas for y and z, plug them into my constraint equation, and that then gives me this equation then in a single variable. And of course that's easy to solve, right? You can solving for x there is trivial. Everybody with me? So this is a nice move, right? Something to keep in mind. Once you have relationships between x, y, and z, you can use those to reduce your constraint equation to an equation of one variable, which you can then solve. And then, and again easy to forget, once you know what x is, then these equations tell you y and z. All right. Okay, so we only found one critical point, and here it is, right? It's 6, 3, 2. And then now, is there a second derivative test? Can I classify this? There is a second derivative test for constrained critical points, but it's weird, and we're not going to talk about it in Math 212. Most multivariable calculus courses don't talk about the second derivative test for constrained critical points. It's just a lot. So anyway, we're just going to draw the line right there. Okay, I have a few more things to say. Obviously, we're not going to have time for the 2 constraint stuff. For whatever it's worth, most multivariable calculus courses taught at Duke in the last 20 years that I can attest to have not covered the 2 constraint Lagrange multiplier theorem. I'll just show you the punchline, though. Basically, gradient of f being a multiple of the gradient of g, you just add an extra term to acknowledge that not only do you have a first constraint gradient, but there's also a second constraint, and thus also a second constraint gradient. That's just how the geometry happens to work out in this case. Why, if you want to look at this picture up here and think it through, that's great, no problem, but you're not required. It's not part of Math 212, so we're going to skip that and the example. I am going to say a real quick word, though, about global extrema. Global extrema, when they exist, right? Recall, we have this theorem with 3 conditions that tells me my function does attain a global max. How do you find it is actually a pretty straightforward matter. We know how to find critical points in the interior. Go ahead. We know how to find critical points on the boundary. Go ahead. Then just look at all those critical points. You got to consider the boundary critical points and the interior critical points. The global max you're looking for has got to be one of those. You just check those values. So I do have an example here, but I am out of time. Most of this example is very straightforward stuff that we've already talked about. So I'm going to cut right to the tricky part that does get really weird. But notice I entertain the interior, then I entertain the boundary. On that boundary consideration, I end up with this algebra right here. Details y'all can follow. That's all very straightforward. Here's where a lot of students make a mistake. A lot of students, so tempting, will say, oh, well, this lambda has got to equal to 1. But wait a second. This is lambda 2, and that clearly has to equal to a 4th. How could the same lambda equal to 2 different things? It couldn't. Contradiction. Therefore, there are no critical points to be found. You see the temptation, right? Wrong. It doesn't work because we were sloppy with zeros. This equation does not say lambda equals 1. This equation, and it's not hard to take the right side of the equation, move it over to the left, and factor, etc. And what you'll find is that really all you can conclude is that there's two possibilities. Either lambda equals 1 or x equals 0. And again, you can't just, I don't want to look at that. Right? No fair. Right? You've got to consider all the cases, and this is a perfectly legitimate case to have to consider. And we just blew right past it. So the proper way to address this is to consider cases. Now, there are 3 different cases to consider. X, Y, and Z can't all be 0. In this case, we are, after all, on a boundary. We are looking at where this is equal to 36. That's on the boundary. So X, Y, and Z can't all be 0. So you consider one at a time which ones might be non-zero. Oh gosh, that little thing. Here we go. So let's suppose X is non-zero. If X is non-zero, then it does indeed follow that lambda has to equal to 1. Totally. So we're assuming that X is non-zero. Okay. But then there's no contradiction. We're not assuming anything about Y or Z. So we can't draw any contradictory conclusions about lambda. But I can take this value of lambda here, and I can plug it into these equations. And with lambda equal to 1 in these equations, I can certainly conclude then that Y and Z have to be 0. And once I know that Y and Z are equal to 0, I can plug this into our constraint equation and solve for X. Everybody see what happened there? Now, that was one of the 3 cases. There are, of course, these other 2 cases to be considered. You got to do them too. But notice what we get then is 6 critical points. So I think this is a great example. This is very real world that if you're just a little bit careless with cancellations and cases and inadvertently, playing fast and loose with possible division by 0, right? You miss 6 critical points. So just as a word of warning, please do be careful about that kind of thing. We're out of time. We did finish the course. How about that? We made it. I enjoyed having you all in the class this semester, and see you tomorrow for the last exam. All right, have a good one.